Hi, welcome everyone. I hope everyone's doing well. Today I wanted to go over this paper with you. It is called Global Warming, Climate Change, and Environmental Pollution. Recipe for a Multifactorial Stress Combination Disaster. It is by authors Sarah Zandelinas, Felix Fritzici, and Ron Mittler. I am so sorry if I have mispronounced those names. This is going to be a part one. The purpose of this video is to give everyone the basics of global warming and its effect on its planet. That way, when we get into part two, the why and the basic of understanding is already there. Like with any journal article, let's start with the abstract. And if you've never read a journal article, that's okay. I do not blame you. I know they can look very daunting, but they have what is called as an abstract. This is basically a summary of the paper. That way, other readers can see if they want to read the paper in full or not. You can kind of think of this as a preview, giving a little bit of everything and drawing you in. The abstract, or preview of this paper, goes as follows. Global warming, climate change, and environmental pollution presents plants with a unique combination of different abiotic and biotic stressors. Although much is known about how plants acclimate to each of these individual stressors, little is known about how they respond to a combination of many of these stress factors occurring together, namely a multifactorial stress combination. Recent studies revealed that increasing the number of different co-occurring multifactorial stress factors causes a severe decline in plants' growth and survival, as well as in the microbiome diversity that plants depend upon. This should serve as a dire warning to our society and prompt us to decisively act to reduce pollutants, greenhouse gas, global warming, and augment the tolerance of crops to a multifactorial stress combination. Okay, that was a lot, and if you still don't get it, that's perfectly okay. We will go through everything and I'll make sure everything makes sense. In this figure one of the paper, as I was reading the paper, I came to understand there was a much larger story that needed to get across. So that's why I decided to break up this video into two parts and explain the much larger story. So just like an abstract is a preview of the paper, figure one is going to be a preview to the rest of the video. With that said, let's start telling the story and break down the components of climate change. Before we can start to understand the effects of climate change, we need to understand one main driving force behind it, and that is greenhouse gases. Some of you might have heard this term or seen it in the news, but what are they and why are they so important? Put simply, greenhouse gases are molecules that trap heat and absorb surface radiation. And there are a couple different types of greenhouse gases. Over here in this figure, we can see some of the most common greenhouse gases, starting with CO2, which I'm sure you're familiar with, which stands for carbon dioxide, and this is a chemical formula for it. It's carbon and two oxygen atoms, and no, you don't need to know any basic chemistry for this, just wanted to go over what it is in case you do want to know. There is also methane, carbon and four hydrogen atoms, nitrous oxide, two nitrogen and one oxygen. The remaining three are F gases. So you have hexafluorocarbons, hydrogen, fluorine, carbon. You have parafluorocarbons, phosphorus, fluorine, carbon, and sulfur hexafluorides, sulfur and six fluorines. These molecules, once released, float and accumulate in the atmosphere and create something similar to a blanket that helps insulate the Earth. This is what's known as the greenhouse effect. We can see as solar radiation comes in, it's bounced back up as heat, and then the greenhouse gases naturally trap it. And this is done in a natural process with naturally occurring water and carbon dioxide molecules. This is what makes Earth hospitable and livable for all life on Earth. However, since humans have been burning fossil fuels, there's been an excessive amount of greenhouse gases, creating this a thicker blanket, causing the planet to get warmer. This is what is known as the human enhanced greenhouse effect. And this is what's driving global warming. And although I have explained to you several different types of greenhouse gases, many policies are focused on CO2. And why is that? Well, in this figure here, we can start to break down and understand Why? It is showing the total global greenhouse gas emissions in 2023. And I don't have the specific numbers. However, by percentage, CO2 is predominantly released, causing about 73.7% to be released. The next closest is methane, around 18.9%, followed by nitrous oxide at 4.7%, and then lastly by F gases at 2.7. Now, even though some of these gases may produce a stronger effect than CO2 when trapping heat, it's because since CO2 is produced in such large quantities, we want to focus on this first. Another reason why we focus on CO2 is because its strong correlation with average global temperatures. And as we can see here, figure 1A from the paper, at the bottom is going across time. Looks like it's going about every decade since 1960. On the left, we can see atmospheric CO2 measured in ppm, which we'll get to. And on the right is global temperature anomaly from 0 degrees, which we'll also get into. Atmospheric CO2 is measured in ppm, which refers to the concentration of a mixture, measuring how many of a substance per 1 million particles of mixture. In this case, it's measuring how many parts of a mixture, in this case air, so how many parts of a million parts air, how many of those parts are CO2? And as you can see in 2020, just above 400 parts. Temperature is saying from this 0 point, how much has global average temperatures increased? And as we can see, both of these are exponentially, I know there's a curve here for some reason, but actually both global temperatures and CO2 is exponentially increasing. To put some of this into perspective, I want to focus your guys' attention on this bottom figure here. This is the carbon dioxide concentrations within the atmosphere over the last 800,000 years, okay? And I need you guys to understand, if you guys don't take away anything else from this entire video, you stop watching, you are bored, whatever, this is the one figure that you need to take away and understand, okay? In the last 800,000 years, global concentration of CO2 has gone just, let's say, 175-ish ppm, and it's never gone above this line. This line is 300 ppm. It hit it exactly once here. It looks like 325,000 years ago, roughly, but it never went above it. Because the concentration of CO2 in the atmosphere is so closely related to global average temperatures, we can extrapolate the rising and falling here to be also very, very, very similar to the rising and falling of global average temperatures, and this is what scientists refer to as the planet heating and cooling. We can see these waves. Again, it has never once gone above this line, and we go all the way across. We can see that there's a sharp increase. This is because since humans have started using fossil fuels, the concentration of CO2 has exponentially increased. Do you remember those from math class? Those, trig equations. One goes like this, it's like a half U shape going up. That's exponential. Global concentrations hit 300 around 1913. Now let's think back, let's take a little history lesson. What was happening around that time? Do you guys know what's happening? The start of World War I, and also the Industrial Revolution, okay? And ever since then, it has never gone below that number. It has only gone up. As of 2024, global carbon dioxide levels are 422.8 ppm. And do you see this line? It is only straight up. This is not natural, okay? This is man-made. This is natural. Natural heating and cooling is a lot of life and history here. This is not, okay? And that's why this chart is very important. Pardon my French. We're all on the same page? Okay, good. Let's move on about the elephant in the room. US carbon emissions. In this figure here, we can see the top 60 highest carbon emitting countries in 2019. And carbon emissions refers to the amount of carbon-containing greenhouse gases released into the atmosphere as a result of human activity. And as we can see, this is measured in metric tons of CO2, and this is in billions of metric tons with a B. And we can see that China is number one, but number two is the US at 4.74 billion. And we can see all the different countries and we can see how staggering of a difference these top 3 countries are. What this really is showing is, in this little box here, is the US federal government greenhouse gas emissions. That means just the federal government alone, no citizens. What is the federal government releasing? It is releasing a total of 69.5 million metric tons. And if we extrapolate this just a little bit more, 75% of all of that is just the Department of Defense. The other 25.3 is all other government organizations, okay? It is a problem that one department is accounting for 75% of all the US federal government greenhouse emissions. To put this in perspective, if just this one department of the entire US is put into its own country, the US Department of Defense alone would be 54th biggest producing country if it was a country. That is a problem. The US Department of Defense needs to be regulated along with their carbon emissions. With that, 75% of the 75% is just jet fuel, which is an entire separate problem beyond the scope of this video. Now, from here, from everything I'm going to say from this point on into the next slide is all speculative. But let's think this through. The numbers on this figure only account for what is public knowledge and can be traceable one way or another. How is it traced back to the Department of Defense? Meaning, all the projects the DoD deems as blacklist classified, things that they don't want the public to know, those kind of things are not accounted for or traceable and included in this figure. Again, this is speculative. We know that the DoD likes to hide a lot of projects. In addition to this, anything that goes boom is also not accounted for in this figure. And anything that goes boom produces a lot of greenhouse gases. And I don't know about you, if you've listened to the news or seen anything lately, there's been a lot of things that go boom going off globally, especially amplified or sold because of the Department of Defense. And all of those numbers are still producing greenhouse gases into the atmosphere. They're just not being traced. So if we put all of that together, this number is very, very likely to be much, much higher. Probably around 500 million, putting it in the same level as Mexico, South Africa, Saudi Arabia, Canada, Indonesia. And along with these countries, this is just one branch of the entire federal US government being in line with the top 10 countries producing carbon dioxide. That is a problem. This is not speculative. This is why agencies such as EPA need to be, one, not corrupt, and funded and invested in to regulate these kinds of emissions. With that said, let's move on to the next slide. Okay, while we're here, let's take a deeper dive on carbon. This is a simplified illustration of the carbon cycle, which describes the flow of carbon on Earth and includes human activity. If we start here in the atmosphere, we can see that carbon is uptake into some plants, and then from there, we see that carbon also goes into the soil. We can see that carbon eventually finds its way into the oceans, and within the ocean it has its own cycle. Within the oceans it can go to a couple different places. One of those is deep ocean, and after that it goes into sediment. From there, through various ways, carbon is released back into the atmosphere. A lot of the ways is through human activity, and all along this cycle, of course, other living organisms consume and release carbon. And this is the natural flow known as the carbon cycle. There are places where large amounts of carbon are stored and are known as carbon sinks. This includes fossil fuels, which are extracted from sediment. These reservoirs also include the oceans, vegetation, the soil, and the atmosphere. Fossil fuels, by the way, are a non-renewable energy source formed by buried organic matter millions of years ago. You can think of oil or natural gas. Global governments have been aware of this effect as humans on the carbon cycle. Scientists have come together to form what is known as a carbon budget, which describes a limit of the total amount of CO2 that can be released into the atmosphere in order to stay within a specific temperature range or threshold. This helps make better environmental policies internationally. Put simply, a carbon budget is similar to a financial budget, where Earth has only so much carbon it can spend or release before it goes into debt. In this case, debt is much more complex than just a number. To better explain this, let's look at this figure. It is showing how exactly we have gone over 400 ppm since 1950. Since then, we have spent our carbon in 4 major categories: coal, oil, gas, and land use, which includes deforestation, farming, and inefficient use and structure building. On the other hand, continuing with this metaphor, we get paid in carbon through the forms of carbon, land sinks, and ocean sinks. And as you can see, we have spent a lot more carbon than we have gotten paid, which is why over the course of a very short amount of time on geological timescales, we have spent more carbon, which has led to the overall concentration of CO2 to increase and be above 420 ppm. Again, because of this tight relationship between CO2 concentrations and average global temperatures, we can extend this budget to see how much less we need to spend in order to hit certain temperature goals. And that's kind of what this figure here is showing. Before I get into it, 1 gigaton is equivalent to 1 trillion kilograms, or 2.2 trillion pounds. Now, specifically, if no climate policies were made, and this is more likely an underestimation, we can see starting now, or around this area here, if no policies were made, we're going to be, 1, spending a lot more, doubling the amount of CO2 released, which is going to cause an increase in global temperatures to about 4 and 5 degrees Celsius. Now, if we stick with the current policies that are currently being made, the increase is going to be around 2.5 to 3 degrees Celsius. Again, global agencies have come together to set pledges on the total amount of carbon that can be released before environmental disasters occur. The pledges are around 2 degrees Celsius. Idealistically, we would like to hit 1.5. In order for these pledges to be hit, you have to see how drastic of a change we have to make and spend a lot less carbon by 2100. And these are the exact lines, estimately how we would get there. This may sound ambitious, but I personally believe that it is possible. We just need to put people in power who are knowledgeable, deserving to make critical and ecological policies, and who care about sustainable and hospitable futures. Okay, so I know I keep talking about global temperatures. Let's now talk about it and why it's important. Remember in figure 1a, it showed what seemed to be an arbitrary 0 point. Where exactly did they get that 0 from anyways? Well, in this figure here, it is showing 5 different temperature recording systems for the past 150 years or so. And as we can see, they're all saying basically the same exact thing, right? Between 1850 and 1900, we can see all the temperatures relatively stayed at this line. This is what's known as the 0 line, or the pre-industrial line. It serves as a 0 point for climate policies. This is because after this point, before this temperature average, we can see that there was a slight dipping point, but then it exponentially increased. Again, here is where World War I stands. We increase. World War II is roughly right here. Decrease just a little bit. And then we really heavily use fossil fuels right here. And it has only gone up. So by definition, as it's getting hotter, this is what is known as global warming, or the steady increase in global average surface temperatures both on land and sea. As we stated in the last slide, governments from around the world have noticed this and have tried to address this issue. One of the many things they have done is create an international treaty to try to keep temperatures below 2 degrees Celsius, or idealistically 1.5 degrees Celsius. And this is known as the Paris Agreement, which was signed in 2016 by roughly 195 countries. Unfortunately, due to the Trump administration on January 27th, 2026, the US will withdraw from the Paris Agreement again for the second time. And that's what this second figure is showing us here. As of January 1st, 2025, all of these countries on green have signed and ratified, meaning they've put in some type of pledge and some type of law changes. These countries here have signed it, and the US is trying to quit it. Again, remember, the US is the second biggest polluting country in the world. So to say that this will affect many future generations and life on the planet dramatically, and drastically is a vast understatement. We are accelerating to the point of no return by decades in a span of a few years because of this decision. The regulations and deregulations of the US under the current administration is going to be dramatic. The rest of these slides in this section will explain some of the effects heating of the planet will cause. In climate science, there is what is known as environmental tipping points. These are critical thresholds in Earth systems where small changes can trigger large, abrupt, and often irreversible shifts with significant consequences for the ecosystem and human societies. In this graph, we can see some of the major environmental tipping points as global temperatures go up. This is on here on temperatures, global temperatures as they go up from that 0 point that we've talked about. As the temperatures go up, the more likely it is for these tipping points to occur. And this is illustrated by the different color gradients. So as the temperature goes up, the more likely, or the darker red, these events are going to occur. And some of these events on here are the coral reefs dying off, the West Atlantic ice sheet collapse, subpolar gyri overturning collapse, mountain glaciers retreat, the Atlantic Madrino overturning circulation collapse, the Amazon rainforest dieback. These are all major events. And we can see it's predicted between 1 degrees and 1.5 degrees that this will occur. That's how you read this figure. On this one, it says between 1 and 3 degrees Celsius. It's indicating that this bar might shift downwards if the models were too stable and didn't account for everything. Again, this one's saying this will lower with additional deforestation. It's more likely to occur as we have less Amazon rainforest to begin with. One of the main reasons global policies is trying to stay below 2 degrees Celsius is because once we hit 3 degrees Celsius, it's predicted that 3 major environmental tipping points are going to occur at the exact same time, or if not within a couple of years of each other. And so we've hit this 2 degrees Celsius point to try to stay within the bounds of these other events not occurring. However, as of October 2025, we reach our first environmental tipping point, and that is the collapse of coral reefs, where nearly 80% of them have already collapsed. Corals, which are the backbone of coral reefs, are a very sensitive organism, meaning they have a very small window of environmental conditions in which they can live in. If the ocean warms by even just 1 degree Celsius, they start to bleach, and as they hit 1.5, they are starting to die. And this is what's happening in the oceans as it's getting hotter. And you can think of coral reefs as the tropical jungle of the oceans, where coral reefs support an extraordinary level of marine biodiversity, providing habitat for nearly 25% of all marine species, despite them covering less than 1% of the ocean floor. In this image here, we can see what coral reefs are meant to look like. There's diversity across all reefs, but some similarities of very diverse, a bunch of different colors, a lot of different fish, a lot of different types of species that live here. And this is what we're seeing now today is 1, they're bleached, but then 2, they're dying, and we can see that there's just no life here. And that's simply because the ocean has gotten hotter. Besides these places providing spaces for marine species to live and thrive, they also provide some of these other benefits, as they act as natural breakwaters, reducing the effect of wave energy and erosion, and lowering the number of people affected by flooding by 45%. They provide a natural food source for millions of people. They provide many natural bioactive compounds sought out by medical institutions, meaning they provide molecules that are already readily available, ready for your body to use for medical purposes. They also have a significant impact on cultures and religions. They provide for local and global economies, accounting for a little over 15% of the global economic system, and many, many other benefits that we now are losing and have lost because of rising global ocean temperatures. Many of you have seen or felt the effects of global warming already, whether it be in the form of polar vortexes or seeing northern lights in locations where they haven't historically been in millions of years, or through extreme heavy precipitation or stronger storms, or even drier and longer droughts. This is because as the planet gets warmer, it causes a redistribution of the water cycle, making drier places drier and wetter places wetter. This also causes extreme weather events to occur stronger and more frequently. Extreme weather patterns are unusual, severe, or unseasonal weather events that fall at the extremes of the region's historic climate distribution. And in this figure, we can see how global warming has affected these specific extreme weather events. For example, a warmer atmosphere means more energy for storms. Storms then are projected to become more frequent and stronger. It is also causing more rain and snow to fall in heavy and intense quantities. Extreme rainfall has increased flood risk. At the same time, it is causing heat waves to become more frequent, hotter, and last longer. And in figure 1b of the paper, as we can see here, we are seeing the number of droughts that are occurring and the number of extreme temperature events that are occurring. Again, across time, we're seeing the same exponential increase that we've seen in CO2 concentration and global surface temperatures. Another vitally important system affecting global and local weather patterns is what is known as thermocycling circulation, which is the movement of oceanic warm and cold water over the entire globe. It is driven by surface heat and freshwater fluxes. The THC provides circulation of nutrients and stabilizes global weather patterns. Down below, we can see the entire THC, where the red indicates warmer surface water and the blue indicates deeper, colder ocean water. You can think of this movement as a conveyor belt, moving again nutrients and water. On this conveyor belt, there are 3 different exchange sites, one occurring here in the Pacific Ocean, where deep water rises, it circulates to the top, becomes warm water, and moves this way along the current. Over here in the Indian Ocean, it starts in the Southern Ocean, moves its way towards Africa and towards India, in between Madagascar, where the deeper water then becomes the surface, it becomes warmer water, and continues along this route. And again, the warmer waters from the very tips of the Southern Ocean move its way towards into the Atlantic Ocean, moves its way towards the Atlantic coast of both the North and South and Central Americas. Then it makes its way towards Europe, just on the west side of the UK, the southern side of Iceland and Greenland, where the water, instead of going up, it goes down because it's surface hot water. It becomes cooled, and the cooler the water then flows down and circulates down into the Southern Ocean. And this is when it continues its loop, and this again is the entire THC. And in this part of the conveyor belt around Greenland and Iceland, in the northwest parts of Europe, it is known as the Atlantic Madrinal Overturning Circulation, or the AMOC, which we saw in the previous slide. And in this figure here, it's a very complex figure, we can see overall it is telling us that the AMOC is weakening because the ocean water is getting warmer, meaning this part of the conveyor belt is not able to complete and do its entire cycle. And again, as ocean temperatures continue to rise, the likelihood of the AMOC collapsing also increases. Oh, by the way, once the collapse occurs, it would take thousands of years to fix itself. And luckily for us, it is predicted to occur in our lifetimes. It's estimated to occur between 2055 and 2069 if we don't do anything about it. And to put this into perspective of how important the system is, if AMOC were to collapse, here are some of the things that are guaranteed to occur. First, it would keep cooler waters in the north here, which would cause several cascading effects. The first of which would dramatically lower the average temperatures here in Europe. Then soon after, it would be very likely that the ice sheet itself that stays here would extend its way down until around this area, again, this mid area here. So we'd have an ice sheet here, likely causing another ice age, as well as causing permanent La Nina years in this region. This also would cause sea levels to rise and flooding to occur all along the Atlantic coast. This collapse would also, the equator is roughly right here, also known as the tropical region, would move southward because of the frigid temperatures up in the north. This would cause the seasons to change 180 degrees as well. And so much more would happen because of this collapse. Okay, at the same time that all of this is happening and all of this is occurring, we are also seeing a dramatic loss of glaciers worldwide. And this reason is actually pretty straightforward. That is because glaciers are a dense body of frozen fresh water in the form of ice that moves downhill underneath its own weight. Glaciers are formed by continuous snowfall that eventually packs itself down into ice. There are a couple different types of glaciers, and some people might get this confused because they're very similar. I was confused when I was looking into it, but ice sheets are dome-shaped glaciers that cover 50,000 square kilometers or more over land and move in all directions. Similarly, ice caps are dome-shaped glaciers that cover less than 50 square kilometers and still move over land in all directions. I learned that ice caps don't necessarily have to be at the tips of mountains. But as the planet gets warmer, so does the rate of ice melting. This is all important for several different reasons, most of which we won't have time to get into in this video. But one of the main reasons, which we'll get into later, is because glaciers hold a vast majority of frozen fresh water. And once it's melted, it either creates a lake or flows eventually into the ocean, which we'll get into in both of these figures. In this first one, we can see, well, it kind of just speaks for itself. In 1919, this is an image of a glacier in Switzerland, and we can see here all of this, it probably protrudes out here. All of this is glacier, right? And all these have snow caps, and there's more snow back here. And this area is very Arctic-like. In 2025, this is a picture in the same exact spot, but we can see there is no longer a glacier here. This is only 100 years. In geological timescale, this is nothing. This is a fraction of a blink of an eye. The glacier here is remaining here, and that's all that remains. There's no snow here. This is actually now what presumes to be some type of vegetation that wasn't there before. There's now, you can see where this area once stood now at the very bottom of the base is a lake, and there's probably some glacier milk coming through here. But again, this is dramatically a different environment. And this is simply because the planet has gotten warmer over these past 100 years or so, because again, we have this human enhanced effect on global warming. And over here on the right is a detailed image of the entire globe. If all the terrestrial ice melted, if that were to occur, the sea levels themselves would rise by 70 meters. And we can see this is not a map that I'm familiar with. It might have some similarities. As we can see here, parts of Australia is now under in the ocean. We can see the expansion of the Mediterranean Sea, creating new seas and expansion of what is there. We can see what parts of Russia were once melted are gone. We can see parts of Greenland are entirely melted, the ice sheet's gone. The bay here in northern Canada is expanded. Parts along the Atlantic coast of the Americas are now flooded. The Amazon River is enlarged. Here, the Mississippi Basin and all of Florida, gone. They don't exist anymore. And other finer details. Many islands are gone in this. Antarctica is now a chain of islands with some continent. Please note that there are several other equally important effects that occur as the planet warms up. We just don't have time to get to all of them in this video. Now, let's take a deeper look into how the majority of land is used here on Earth. In this figure, we can see exactly how Earth is divided, and as the name suggests, the blue planet, 71% of Earth's surface is considered ocean. This leaves everything else be considered land, which accounts for about 29% of Earth's surface. Of this 29%, 76% is suitable for human habitation and use. This is also known as hospitable land. which is probably the land that you're most familiar with and think of when you think of land on Earth. However, 24% of the land is not hospitable for humans, and it's covered in things such as glaciers, deserts, salt flats, etc. Now, I'm sure most of you think that since humans have such a large effect on the globe, we must take up most of the land for ourselves. And in some sense, that is true, but realistically, roughly 55% of all humans live in urban areas, which take up roughly 1% of all hospitable land. This little sliver, 55% of humans live here. This leaves the remaining 45% to be scattered across rural lands, where the land has low population and infrastructure densities relative to the area they occupy. You might wonder, why don't you see any rural land as a category on this chart? I see agriculture, forests, shrubs, urban land, and bodies of water, but no rural. That is because rural land is encompassed within agricultural land, as the primary use of rural land is inherently agriculture. Agriculture land encompasses all the land used for agricultural purposes. It's worth noting, depending on the classification material for urban land or how specific organizations categorize lands differently across the globe, land with medium densities, such as suburban lands, can either be considered rural land or urban land. The rest of this figure breaks down how specifically agricultural land is used. I just want to point out that 80% of the agricultural land is not directly used for humans. It's used for feed for animals and textiles. Also, I want to note that this data is based off a couple years ago, and the numbers have shifted today, where urban land is between 2.5 and 3%, and these numbers shift because of human activity. Forests are less because of deforestation. Agricultural land is closer to 40%. However, the relative size to each one of these lands is still the same to one another, meaning hospitable land is still the largest percent. And these numbers are changing as global warming increases. It increases sea level rise, which causes this to decrease, all of which is due to human activity. With all that being said, let's take a look at figure 1C from the paper. Again, across time, as world population increases, arable land directly decreases, causing an inverse relationship. Arable land specifically refers to the land as currently being capable of being plowed and includes all land under temporary standing. However, it does exclude any land that is in permanent use, such as land for fruit trees or permanent pastures, and it is part of agriculture. Because of this inverse relationship between world population getting bigger and less amount of arable land, it demands for an increase in efficiency in the remaining land that we have. Traditionally, in many regions around the globe, farming has predominantly relied on monocultural practices. This approach involves cultivating a single crop at a time on the same land. This has led to the attraction of several different species finding ways to survive, seeing as their native environments are continuously being lost. These species find resources in vast plots of land with a single crop. And to keep up with efficiency needs and address lowering crop yields due to these species, farming industries have increasingly relied on the use of pesticides, herbicides, fertilizers, and genetically modifying their crops. However, it comes with lots of drawbacks. The farming industry uses chemical pesticides, which are a substance or mixture intended for preventing, destroying, repelling, or mitigating any quote-unquote pests. There are two main types of pesticides. One intended on targeting plants known as herbicides, and the other intended on targeting insects known as insecticides. Specifically, neonicotinoids are a class of insecticides that are neuroactive or brain active and has a similar chemical structure to nicotine. Down below here in this picture, it's showing several different ways neonicotinoids are affecting the environment. However, this can broadly be used to explain the effects of pesticides and herbicides on the environment as well. Because these chemicals are inherently water soluble by design, this leaves any substance on the surface to flow as runoff into bodies of water. Also, these chemicals can be released as dust coating seeds during planting. This dust can reach off-target sites and non-target invertebrates. Lots of times these chemicals are sprayed, and when they're sprayed, that has a chance of targeting and exposing non-target areas and invertebrates. When these chemicals are applied, and especially when they get into non-target areas, the plants then uptake them to different parts of the tissue and can be put into pollen or nectar or other tissues such as leaves, which other non-target or direct target insects then consume and affect the ecosystem. Again, since these chemicals are also inherently water soluble, the chemicals can leach into the soil. The leaching into the soil then can go into our groundwater system. These chemicals are also long lasting, so once they're sprayed, they're in the area affecting the environment for many months to a year after one spray, and most of the times they're sprayed multiple times. Similar to the dust, pesticides can drift in the wind and contaminate other non-target soils off into the distance. Also, when these chemicals are in the soils, they have a chance to target non-target habitats and creatures, such as ground nesting bees, to be contaminated and killed. And these bees and any non-target pollinators are crucial to the system at large. So it's important to think of how we can improve this system and rely less on chemical pesticides. As we can see, they have a whole host of problems in the environment. All of these contaminants eventually makes its way into our food supply, especially when they're contaminating water sources, or they're contaminating the foods that we directly eat, or indirectly through the environment. Now, just like all living things, plants needs a certain set of conditions for them to grow. For plants, the law of the minimum states that plant growth is dependent on the least abundant resource available, even if all other resources are in abundance. And in this little tiny illustration here, we can see that if yield is the same as the amount of water this bucket can hold, and the sides or the walls of the bucket are things that the plant needs, such as sunlight, magnesium, water, etc., then the maximum amount of yield or water that a plant can produce is dependent on the lowest wall. And it's important to note the lowest wall, or the lowest abundant resource, one day or 1 week might be the most abundant, or just a middle wall another day or another week, and these conditions are constantly changing. Also, the longer a single plant is cultivated in the same specific area, more of the same resources are extracted from that specific environment. And the less those resources are replenished naturally back into the soil and overall the environment. This is why you might see some fields change their crops every few years and or leave the land untouched every so often. It's all an effort to replenish the resources lost. Due to this and increasing efficiency demands, the farming industry supplements these plants with fertilizers or plant food, which specifically dissolves in water and sprayed over plants, similar to the pesticides. However, a more natural way to vastly reduce the use of pesticides and fertilizers and naturally increase efficiency is through polyculture farming. Polyculture farming is the practice of cultivating multiple crops within the same space. This vastly reduces the need for pesticides and fertilizers. This is also the same advanced farming practice that Native Americans used before colonists thought them as lesser and cleared them out along with their farms to set up monoculture farming instead. And in this figure here is a simple example on how polyculture farms work. Put simply, these target plants are surrounded by different groups of plants that all help it in some sort of way. You have haven plants, which support natural pollinators, predators, and parasitoids. Trap crops that attract pests away from the target crop. You have screening crops, which stops pests from directly seeing the target crop. And you also have aromatic companion crops that deter pests from seeing the crop through odors rather than a physical barrier. And then you also have groups of plants that help bring nutrients back into the soil. For example, legumes, which are known to be part of the pea or bean family and can fix nitrogen into a usable form from the air and add that into the soil, acting as a natural fertilizer. And up in here are all the different types of legumes you might see or are familiar with. On the bottom right here is a small example of how this system can be used. And I'm not going to go into specifics of all of these plants. Please feel free to pause the video to see all of them. But for example, dandelions attract pollinators, onions are a pest deterrent, clovers again are fixing nitrogen, and rhubarb is a natural weed suppressant. The system can also be expanded to have multiple different target groups, creating a whole web of plants. And when compared to monoculture farming, polyculture farming increases nutrient efficiency, water efficiency, biodiversity, and soil functional microorganisms. And it also decreases soil-borne diseases and soil erosion. One of the biggest drawbacks that you might hear from fertilizer and farming adjacent companies is that this farming is not able to be grown at scale. But we humans already have done this before, and we can certainly do it again and potentially even better. We just have to listen to science and have the environment's health first on every decision instead of money. Speaking of which, agricultural productivity is a ratio measured by the amount of yield of product per unit of agricultural input. In figure 1F of the paper, we can see the projected change of agricultural productivity within specific regions across the globe, comparing the years of 2080 to 2003, where the darker the red the color, the less productive it is, and the darker the green the color, the more productive it is. Areas right here, and between the Tropic of Cancer and the Tropic of Capricorn, areas are going to become less productive. In the areas outside of that, so down here in the southern part of South America and Australia, New Zealand here, and then northern parts of Central and North Asia, basically all of Europe, and the northern parts of North America, are we going to become more productive? This is because of climate change, which is the long-term shifts in temperatures and weather patterns. Today, this process is driven by global warming via human activity. This is causing all climates to become hotter in general. In a very specific case, this figure is showing the areas where wine grapes are currently being grown and how they will shift in the coming years. Areas in red are currently areas suitable for wine grape production. However, by 2050, they're going to be lost. Areas in blue will be the new areas suitable for wine grape starting in 2050. And then areas in green will be areas suitable for wine production through 2050. And as you can see, in the general sense, this area, all this wine production is going to move more north, as this area is typically known for its colder regions. It's now becoming warmer, so it's going to become more suitable, and this area, what's typically suitable, is going to become too hot. This will directly affect the total market value of goods and services of a country, also known as the gross domestic product, or the GDP of a country. Currently, wine industry accounts for roughly 1.9% and 1.1% for Spain and Italy, respectively. Because of climate change, wine will no longer come from those countries which are known for wine, Spain, Italy, France, and instead we're going to get wine from Germany and Belgium and the Netherlands, Czechia, Poland, parts of Britain, Denmark, and even Sweden. It does seem that wine production in France overall and in general are going to hold. However, in the local economies, southern France is going to get hit the hardest, as they're going to lose wine production, but northern France is going to be able to support the loss from southern France. But this is how, among many other factors, climate change is going to affect the GDP and the economies of countries. From land, we jump back and make a splash to the seas. Water, more specifically freshwater, is arguably the most important resource that we have on Earth, as every living creature depends on it in order to grow. On top of survival, humans have found numerous ways to consume and extract fresh water, the scope of which is too large for this video. Similar to this carbon cycle, Earth has a global system for the flow of water called the water cycle, which is also greatly affected by human activity. And we can kind of see that here in this figure. So starting in the atmosphere, water is held. At a certain point, it precipitates. It can precipitate either in the form of snow or water. From there, water finds its way to the ocean, where the majority of it is stored. While there or on its journey to the ocean, it can be used in living things, including humans, or evaporated directly back into the atmosphere. That, in a nutshell, is the water cycle. And similar to the carbon cycle, there are places within the water cycle where large amounts of water is stored. Think of the groundwater, the oceans, and as we can see in this figure, this is showing all the water on Earth and where that's located. We can see that roughly 97% of all water is some sort of salt water. That leaves only 2.5% of water to be considered freshwater. Of that 2.5%, 68.7% is frozen in the form of glaciers and ice caps. Another 30% of freshwater is in groundwater. That leaves only 1.2% of 2.5% to be water on the surface or in some other form. Of that 1.2%, another 69% of that water is frozen in either ground ice or permafrost, which means the remaining percentages of fresh water are more of what you and I probably know of more than these other forms, besides maybe oceans. And that is lakes, taking up the majority of which, then soil moisture, which we don't really necessarily see, then there's water in the atmosphere, then there's swamps and marshes, and then there's rivers that we all know, and then the rest of the remaining water is in living things. So it's extremely important on how we use our fresh water, seeing as we really don't have that much. And for the vast majority of human history, the natural flow and relatively quick abundance of the water cycle allowed it to be deemed as a natural resource. Some key examples are solar, wind, geothermal, and the air we breathe. Along with that, in the same vein, there are places or reservoirs within the freshwater cycle that are also deemed to be renewable, such as lakes, rivers, and groundwater. And these are also, along with other not renewable resources, and the water cycle in general, are greatly affected by human activity. And these renewable freshwater reservoirs are the backbone to all land, organisms, and environments. But within the last century, due to over-extraction, inefficient use, pollution, etc., these three resources and a few freshwater resources have drifted into the non-renewable resource category, which is a resource that has a fixed quantity on Earth and or cannot be replenished fast enough to meet consumption demands. Some examples are minerals, land, and fossil fuels. Like we recently just said, groundwater, freshwater, timber, food, and biomass are now leading and sliding towards the non-renewable resource category. To put some consumption into perspective, let's look at this graph here, figure 1D from the paper. It is showing again across time the amount of global freshwater use and the renewable freshwater resources. Again, we're seeing another inverse relationship here. And this data stops around 2014. I just want to put that into perspective, how much society has advanced since then. In 2014, that's when iPhone 6 came out. That's also just shy of 1 year when the global population hit 7 billion people as of 2025. The global population is 8.23 billion people on Earth, all of which, by the way, need and depend on fresh water to survive. This is also a decade before AI was widely available and used by global companies. So just like every other resource, it is vital how we use and build structures to use resources sustainably. And that means specifically building structures to meet the needs of the present without compromising the ability of future generations to meet their own needs. Sustainability is a current global challenge humans face if we want to continue calling Earth our home. Before AI, the largest sector extracting fresh water was agriculture at about 70%. Currently, AI extracts more water and is expected to use more resources, including electricity, over the next couple of decades. Which, by the way, AI is a computer system with human-esque-like intelligence with the ability to perform complex tasks such as reasoning, decision-making, problem-solving, perception, language understanding, and a lot more. AI requires large amounts of resources to function, specifically fresh water and electricity, which current numbers are best estimates based on indirect energy and water uses, as the specifics are not released to us and are hidden by these companies. In this picture here, we can see global projected water withdrawals for AI through 2027. AI alone will consume between 4.2 and 6.6 billion cubic meters of water. That is equivalent to 4 to 6 times the annual withdrawal of the entire country of Denmark. At the same time, AI is also projected to use 370 terawatt hours of energy. This is equivalent to 44 nuclear reactors running 365 days a year. This most likely a vast underestimation, as all current AI projects from the government are not included in these estimates, and our increased dependence on AI are only going to make these go up. We are going to run out of fresh water to use, and unfortunately, the current administration of the US in December of 2025 has prohibited the regulation of AI in any state. I cannot express to you how much AI needs to be regulated. The fact that it is illegal to regulate in all 50 states is a dire warning and exponentially increase environmental disasters across the globe. So where is all that water going? In short, it's mainly used for electricity. The majority of water is used for electricity, and also to cool the servers and computer parts, where indirect usage for electricity is considered scope 2 water, and water used to cool the data servers is direct and known as scope 1 water. Due to the complexity and intense computing, the components can overheat, and if they are at high temps for too long, they start to not function properly and eventually break. Specifically, these components are the central processing unit and the graphical processing unit, or CPU and GPU respectively. The CPU is the key part of the computer responsible for interpreting and executing instructions from software and hardware, acting like the brain or control center for the computer. Whereas the GPU is responsible for rendering and processing images and videos to be displayed. It acts like the visual system for the computer. Before AI was used in these data centers, air conditioning alone was enough to cool the servers from overheating. Now, because of how intense these operations are, specifically on the CPU and the GPU, air conditioning alone is not enough to cool these racks fast enough to keep up with these demands. A cold plate has been added over these thermal components to exchange heat through fresh water. And we can see in this figure here, this is the general idea of how scope 1 water is used in an AI data center. So a cold plate is added over each GPU and CPU, There can be a CPU here, GPU here, CPU here, GPU. You get the idea. There can be, 10 to 20 on one of these racks each, and then there's rows of racks, then hundreds of racks in the server room, and there's like multiple stories. You can see how this gets exponential. And of course, it also needs electricity for all this to run. Okay, so water then is piped in through these cold plates. It takes the heat, it goes in as cold water, and it leaves as hot water, and goes into this hot water system. Cold water is also pumped into the AC units to blast cold air out, leaving hot air, going to the hot air exchange. Hot air exchange, hot water goes outside of the system, outside, where it goes to a cooling tower. The cooling tower allows the water to evaporate as steam and introduce more cool water, the remaining water that doesn't evaporate as steam, to go back to a chiller to keep it cold and restart this process over again. And that, in essence, is where water is being used for Scope 1 water. I need to say, in this model here, 80% of the water in this system is evaporated straight up. There's not even a turbine here for the steam to generate electricity. Although I think Scope 2 water is a bigger problem, we simply just don't have enough time to get into it in this video. We will be focusing on Scope 1 water instead. One way to use less water in the data center is to use what is known as non-conductive cooling liquids. These liquids are unable to carry an electrical current through themselves, such as mineral oil, and they're used to cool electronic devices. So in this diagram here, we can see instead of having all the servers aligned on a rack and then having cold plates on over each one of these components, the server or the computer themselves are placed within this liquid. And I know that's going to break some of your brains. How can you place electronics in a liquid and for it to still work? Trust me, it does. It's because it cannot carry an electrical charge. So it's able to function properly. It functions as if it were air. The only difference is that the heat now is going to be directly transferred into this non-conductive cooling liquid. Some water is still going to be used for heat exchange to make hot water cold, but it's going to be significantly less than this entire system. I just want to leave you with this question. Who does the water belong to, if anyone at all? Okay, continuing this conversation about human activity on the environment, I would be remiss and the conversation would not be complete if we did not talk about plastics. So, what exactly is a plastic? Well, in short, plastics are an aggregate or clump of polymers. Okay, cool, a bunch of different polymers put together, but what is a polymer? A polymer is a large molecule made of thousands of repeating smaller subunits in a specific arrangement known as monomers. Plastics are created by chemically binding those monomers together to form a long chain or a polymer, and this whole process is known as polymerization. Okay, so that's what a plastic is. You might ask, what exactly do plastics have to do with the environment and why are they so detrimental? Well, first, many of these monomers are derived from fossil fuels, meaning that almost every plastic ever created needs oil to create it. So I want you to think of this. Think of all the plastic that surrounds you in this current moment. It could be plastic within your phone, within the device that you are watching this on. It could be a plastic mug that you have, maybe the plastic in your headphones, maybe plastic in your wires or chargers, maybe the plastic in your seat. Plastic is virtually everywhere, okay? Now, I want you to imagine that plastic just in the surrounding area that you reside in right now. Now, imagine all of that as oil, okay? That's what plastics are. But it's not only just oil. No. Plastic companies have to add other chemicals known as additives to stabilize, increase its resistance, for its color, help shape it exactly. However they want their plastic to come out with, they have to add additives in order for that to happen. And luckily for us, just kidding, that was a joke, the vast majority of these additives are toxic. And studies have shown that there can be upwards of 20,000 different additives in a single plastic object, with the average number of additives being a lot higher than you may think. One specific group of additives are known as forever chemicals or PFAs. These synthetic compounds have great resilience to degradation, because they have what is known as a carbon-fluorine bond. Now, I want to show you this picture here of PFAs, and don't get scared. You don't have to know a lick of chemistry to understand this, okay? These segments here, where you see a C and a line and an F, this represents carbon bonded to fluorine. And this is the bond that we are talking about. It's the carbon-fluorine bond. This is what makes plastics last for hundreds of years not being degraded, making up the backbone of the polymer. But just like every other solid material, degradation does occur, and degradation is simply a fancy name for the process of something, or the plastic, being degraded or chopped into tiny pieces. Some of these ways include the following. So we have photodegradation, caused by the absorption of UV light or sunlight. We have thermal degradation, which occurs when a material is exposed to heat. We have hydraulic degradation, which is caused by the repeated exposure to waves or water over time. And we have what is known as mechanical and physical degradation, which occurs when a material is exposed to like a physical stress, such as pressure. And over on the right here is the entire process of plastics and the life cycle of plastics, starting with, extraction for the raw materials, oil. The oil then is distilled, so it becomes more of specifically what the companies need. Then it goes underneath polymerization to make really, really, really long chains. These long chains are added together with additives and molded into the desired shape, creating the plastic product. Now, this product can go of one of three paths. Can go and 12% of it is incinerated. It can go and be recycled, where this can be like a loop here, where it's recycled, washed up, downcycled, and recycled again. This can repeat a number of times. Eventually, though, however, it does get thrown away. And the third path here, they both lead to the landfill and oceans. This is not me saying you shouldn't recycle. That is not what I'm saying. I'm just showing the pathway. This also is a better demonstration of what is known as the carbon footprint for plastics, of a single plastic. All of this is included, and this here, landfills and ocean, needs to be expanded, which we'll expand in the next two slides, because it has a much bigger scope than most you may think. Because the majority of plastics takes hundreds of years to break down, it's important to consider where it's going and how it's going to affect the planet that entire time. Unfortunately, a lot of plastics end up in the ocean and landfills, keeping it out of sight for many of us, but having very real consequences on the aquatic ecosystems and ultimately us. Because of ocean currents, plastics and rubbish end up in specific zones in the ocean known as garbage patches, which most of these garbage patches are primarily made up of plastics, where debris eventually sinks to the ocean, causing havoc all the way down and on the seafloor. And in this figure, we can see all the specific sites within all the oceans of the Earth where these garbage patches exist. And we can see we have some in the North Atlantic, some in the South Atlantic, in the Indian and Southern Ocean. We have some in the South Pacific, and we have the densest accumulation here in the North Pacific. And you might have heard of the Great Pacific Garbage Patch. That's what this garbage patch here is. This figure here shows some specifics of the Great Pacific Garbage Patch, and this is to scale. So we can see this is the west side of North America. We have Mexico, San Fran, Vancouver up in here. Here's Hawaii, and we can see like this is the size of the garbage patch. It is 1.6 million square kilometers, accounting for about 3 times the size of France and about 2 times the size of Texas. This is just the surface rubbish, not including millions of plastic debris that has already landed on the seafloor or wreaked havoc for thousands of species. Now, remember about degradation? Well, when plastics are between 5 millimeters and 1 micrometer, it's known as a microplastic. When plastics are between 1 micrometer and 1 nanometer, it's known as a nanoplastic. Put that into perspective. Between 1 centimeter and 0.1 of a meter is a golf ball. A virus is less than 1 micrometer. and DNA is to the scale of nanometers. And it's important to note that nanoplastics are on the cellular and molecular levels. Lastly, I wanted to show you this figure 1e from the paper. Across time, microplastics in the ocean are going up. It's actually exponentially increasing from the exponential we've been seeing all along in this presentation. We can see that pesticide use is steadily increasing, and we can see that fossil fuel consumption is also steadily increasing from 1990 to 2017. While degradation explains how, leaching explains specifically the process by which a substance or chemical is extracted from a solid material into a liquid. I hate to bust your bubble, but all plastic water bottles or containers are leaching plastics and additives directly into your drinking water, especially if those plastics are heated or have any sort of fat with it. And microwaving any food in plastic is exponentially leaching chemicals into your food. Remember, there are upwards of 20,000 additives in each plastic? Yep. Now, I want you to think about the delicious, almost too perfect rotisserie chicken. Those rotisserie chickens, they're 1, sealed and wrapped in plastic. Then 2, the chicken itself has some sort of moisture and liquid along with fats. And 3, is stored underneath the heat lamp. All of these are perfect conditions for plastics to be leached into our foods. These chickens are basically sitting in a bath of plastics. Just throwing that one out there. And that's why it's so important that we are aware and we educate the public about plastics and chemicals and additives. This next figure is going to explain bioaccumulation and biomagnification of a specific contaminant that get in and stay within our bodies. And again, this can be also used for pesticides and herbicides and fertilizers and heavy metals that we've already talked about. There's also thousands upon millions of other contaminants in our environment. It's kind of ridiculous. So bioaccumulation is the process where one species over the course of time accumulate that one specific contaminant just because they are exposed to a contaminant across time. Whereas biomagnification explains the process at each increasing tropic level, the organism is going to gain a significant increase in the toxic chemical. That means if we start here at the plant, due to previous exposure, the plant is going to have a very small level of contaminants. Then these grasshoppers are going to eat the plant, but they need a lot of plants to survive. So these grasshoppers are going to have more levels of contaminant because they eat a lot of plants that have low levels. Then at the next level, these smaller birds, they need a lot of these grasshoppers to survive. But again, these have a bigger amount than this level. So then these birds are going to have a significant level higher than the grasshoppers. And this works its way up through the system. And if you don't really understand this, that's okay. The next slide will really get into what tropic levels are, but that's just the general idea of biomagnification. So if we think about the garbage patches, a plastic bottle or any plastic material is exposed to the sun, to the water, to some heat, and other plastics touching it, all of which are causing tiny fragments or degradation to occur in the form of nanoplastics and then leaching, of course, to the surrounding ocean. Just as a heads up. All of these additives are directly being leached into the ocean. Because they are so tiny, remember, they are on the molecular level, the micro nanoplastics are able to uptake into the cell. And this is the real problem here. Every living cell uptake these nano and microplastics. This is why plastics are such a problem to every living cell on Earth. Because when they go into the cell, they cause an increase in ROSs, or reactive oxygen species, and an increase in oxidative stress, which ROSs are an oxygen-containing reactive compound. And they naturally have both a positive and negative roles within the body. However, at excessive levels, or if there's a persistent increase in ROSs that can't be remediated, at excessive levels, it does more harm than good. Which, by the way, ROSs and oxidative stress levels are only going up and up because plastics take hundreds of years to degrade and our society becomes more and more stressful every day. At this increased level, it causes organelle damage and organelle dysfunction. It causes lipid and protein oxidation, and it also causes DNA damage, all of which are vital for the cell to function, to run. And this is why plastics, carbon footprint, is so complex and so hard to nail, because we don't know where these are going. We don't know what animals these are in. We just have to assume it's in every living system. And the only real long-term solution is to stop the use and production of plastics and invest in science to find ways to break down plastics that we already have. All right, the next couple of slides are not directly mentioned in the paper. I thought, however, these would be good concepts to know and allow you to better understand how interconnected we all are. And what better way than explaining what food webs are? Food webs illustrate the interconnection flow of energy among species within an ecosystem. Before we get any further, it's worth noting that food webs can be very complex, be very large, or very small, depending on what section and what species you're wanting to see. There's like a global food web, or there's smaller ones, like this one is the North American grassland and forest food web, and this one is like an ocean food web, but of course there are millions of species, so it's not showing everything. With that said, within this food web, the first third of the food web is where the primary source of energy comes from, and that is the sun. Virtually every system here on Earth starts with solar energy. There are exceptions to this, but we won't be going into that today. This is a food web, and before we get any further, this is a food chain. It's different from a food web, but basically a bunch of food chains are put together to make a food web, and a food chain is one specific path rather than the entire section of the ecosystem. So, species that primarily obtain the energy through the sun through the process of photosynthesis. Those species are known as producers. Now, for the second third of species, these are known as consumers, and there are a couple different kinds of consumers. Species that primarily rely solely on the producers for food are what are known as primary consumers here. I always thought, why are the arrows reversed growing up? That is because it is showing the flow of energy rather than what species eats. So the squirrel is going to eat like berries and nuts, seeds from the producer, but the energy of the berries, seeds, and nuts is flowing to the squirrel, and that's why the arrows are showing this way and not this way. Above the primary consumers, we have what are known as secondary consumers. These consumers primarily get their energy from primary consumers. And this pattern goes on. Then there's tertiary consumers, where primarily the energy comes from secondary, and so on and so forth. We can get quaternary, and then we can get even apex above that. And then the third, and arguably the most important, are known as detritivores and decomposers, both of which break down organic material and release nutrients into the environment. The difference is how they actually go about breaking down the material and at what scale and what size. So detritivores ingest their food just like you and I. We put food inside of our body, break down these materials into smaller portions than that decomposers can directly use, or sometimes other levels can also directly use. Whereas decomposers break down food externally, so they're excreting enzymes outside of their body to digest their food, and then they're absorbing whatever is left back into their body. So their digestion process is external rather than internal. And these are fungi or bacteria. This is more on the macroscopic or molecular level, whereas detritivores are more on the animal level. Again, it's not always the case, but that's just a generalization. Remember in the previous slide, we were talking about bioaccumulation and something about trophic levels. Well, producers is a trophic level. The next level up is primary consumers. The next level up is secondary consumers, so on and so forth. Each one of these distinctions and classifications is what is known as trophic level. So when you look at a contaminant here was going to move its way up through trophic levels. And again, we can see the same thing here in the ocean food web. Starting with the sun, they go to plankton and work its ways up. So within the food web or environments, there are what is known as keystone species. I'm sure some of you have heard of this term and probably know of a few. But put simply, keystone species have a disproportionately large effect on their environment relative to their abundance. There are 4 different types of keystone species. There are keystone resources, keystone modifiers, keystone consumers, and keystone mutualists, and they all play a very vitally important part in each one of their environments. Keystone resources provide essential resources to their ecosystem, such as food, shelter, and nesting areas. And we can see a willow is a type of keystone resource. Next, we also have keystone modifiers. They influence their ecosystem through physical alterations of the environment, creating or modifying habitats that support a wide range of other species. So we can think of the desert tortoise or the bison. They're engineers of the environment, they regulate the environment, and they create some type of physical changes within their environment. Then we have keystone consumers. These are species that maintain ecosystem balance by controlling populations of other species that would otherwise dominate. Think of the sea otter with sea urchins, or the gray wolves with their prey that they feed on. And because of what they do, they allow for diversity. And I know that might sound counterintuitive. The species that these animals rely on overtake the environment and diversity goes down without them, which we've seen at Yellowstone National Park in North America. Next are keystone mutualists. They create reciprocally vital interactions with two or more species where the disruption of one species significantly impacts other and ultimately alters the entire ecosystem. And now there's more than just pollinators, but I want you to think of mutualists as pollinators. And so on the right here, we can see some of the key pollinators, some of the popular ones you may know and other ones you may not know. But bees, for example, and among every single one of these, bats, butterflies, beetles, hummingbirds, these other species down here, they create some type of relationship. They go and take nectar from the plants, allowing for genetic diversity occur when they go to other plants. Pollination is helping new generations of plants on the behalf of bees. This is a whole different science, which we can probably get into, but not in this video. Some of you may be thinking, so where do humans lie on all of this? Humans are none of these species. The whole next slide is dedicated to humans. But I want you to know, in case you're kind of thinking of that, humans are excluded in these types of species. Lastly, we have what is known as invasive species, and these are non-native organisms that have, one, introduced to a new environment by human activity, and they cause harm to the environment, economy, or overall human health. Currently, we are seeing a dramatic reduction in pollinators, including bees, whose effects we are just starting to see. It's vitally important that we keep all of our keystone species, but it's specifically pollinators, because every single plant that we rely on and the environment then therefore relies on and we indirectly rely on, they're dependent on these pollinators for the next generations of these plants to occur. And without them, we would lose all our plants, which would subsequently, these are our primary producers. Remember, the rest of the environment is relying on these producers to grow, and without them, we wouldn't have an ecosystem. So let's talk about humans as a species and understand kind of their role in the whole global environment and ecosystems. Because we as humans have a very complicated and extremely influential effect on virtually every species on Earth. Therefore, humans are known as Hyperkeystone species. They exert profound effects on the ecosystems by influencing multiple other keystone species across different habitats, the environment, and globally. These effects can range from positive to negative. Each one of these effects or actions that humans have is multidimensional. Over here, we can see in this picture here, the effect can be either local or globally or somewhere along this intensity. The effect can either be weak or intense, so again, somewhere along this axis, or the effect can be singular or occasional all the way to continuous. Pattern is in here. And if we look at here in this figure, it's talking about human actions, the direct effects, the indirect effects, and the entire system effects. Each one of these arrows, each one of these things that humans can do comes with a certain set of conditions on these three axes here. For the rest of this slide here, I'm going to be focusing on this image here, figure from one of the papers I sourced. But essentially, this is saying the same thing, but in more detail. But for simplification, we're going to look at here. The first way that humans have profound effect is acting as a super predator or an apex predator. where there are these are species that have no other natural predators and they're at the top of their food web. And they can do that in two different ways. They can do it by lethal means or non-lethal means. In a lethal means, humans, and for this example, act as super predators when they are extracting fish or over harvesting or over farming fish. As they go out into the sea, they have nets. First of all, they drag along the sea floor, destroying havoc on the sea floor. There are millions of square kilometers destroyed every year because of human farming. Entire ecosystem on the bottom of the seafloor gone, let alone for every other reason, especially like microplastics. We are just scraping the bottom, so it's gone, period. In addition to that, humans are also capturing more than just the target species. They're targeting many other species along when they're farming, and they're just dying in droves because they're quote unquote not ideal. They also act as a super predator in a non-lethal sense, and this is when the entire dynamics of the environment change simply through the presence of a human being. This causes what once were predators to move away. And a lot of times wild animals try to run away from simply the sounds of a human being. And that's very profound. That doesn't happen anywhere else to the same effect that humans have. Next, human beings can act as niche constructors. This is where an organism actively modifies their environment in ways that alter selective pressures acting upon themselves and other species. A great example of this is urbanization or the development of cities. You pick a city, anyone, the environment that was there is now essentially gone. Environment that where the city lays is completely different. And the species that did live here, if they were not plants, go outside the bounds of humans, or at least the bounds of the city. Now they're creating different types of pressures on a different type of environment simply because we are kicking them out essentially and creating our own quote unquote environment where these cities now lay. Again, humans can act as hyperkeystone species. And in this example, again, is the Yellowstone, humans decided to remove wolves from the park, which allowed their predator population to overpopulate, which then caused the rest of the environment to get overran by the predator's elk. That then caused a lot of destruction to the environment, and it's not a lot of regulation occurring simply because we removed a keystone species, which controlled a lot of these populations, which allowed diversity and not overgrazing and environments to be over stampede because of this overpopulation of their prey animals. A risk responder effect occurs when a species modifies its behavior in the presence of perceived predation, even in the absence of direct predation. So a good example of this is when we put up signs for whatever reason. In this case, it's ticks. So now the environment that once had humans are now deterring humans, and this is allowing a new set of conditions to occur, a new set of populations to run, because now humans are not occupying this area. And then a pseudo-mutualist is an organism that provides a benefit to another organism as a byproduct of selfish actions that directly benefit itself. So humans do this in many different ways, and we can see it in this example, but humans will build some type of nesting for an animal, such as a bird. This will allow other species to rise and allow nesting to occur. For us humans, it's usually extraction or saving of a species, creating some form of mutualistic benefit. Only a pseudo-mutualist, because then humans can stop at any time when this doesn't benefit us, or we found other ways to extract whatever we needed. Then the mutualistic relationship disappears. I just wanted to say, if you stuck this far, thank you. If you could please take like 2 seconds, like and share the video, it would mean a lot to me and really help make science accessible to others. And if you like this kind of content and you want to see more, consider subscribing, but that's completely up to you. Secondly, you might be asking, what was the point of talking about carbon and heating of the planet and farming practices and how we use fresh water, plastics, and the basics of ecology for roughly the past 90 minutes? What's the point other than like teaching us and getting to know about science a little bit more and ecology and how we're playing a role in the environment? Well, that's because we are seeing a severe decline in tens of thousands of species. and the drastic increase of the number of species that are threatened with extinction. Amongst the next 3 slides, I'm going to be going over that. Guys, it's a problem. I don't know how to put that in any other way, but then this is a problem that we need to address 20 years ago, okay? If not tomorrow. In these 2 figures here, we can see on the figure on the right is the total number of species threatened with extinction. And it goes by certain categories. We can see roughly on this one, it's 47,187. The majority of those are plants, with the second biggest category being vertebrates, like you and I. We have a spine. And again, this is also showing the same thing. It's saying more than 47,000 are threatened of extinction. It's breaking down by amphibians, mammals, conifers, reptiles, coral reefs, and a bunch of different other categories. It's important to note, although both of these figures are true and very accurate, it is more likely than not, by a very significant margin, that this number is a significant underestimation of the total number of species at risk. That is because these are the number of species that we as humans have been able to observe their populations. There are millions of other species that we just haven't been able to count. 1, because we don't know of. 2, because it's hard. There's lacking funding. There's a lot of geopolitical reasons. So this number is probably a lot higher. Of all those species that we have been able to observe, it's what is known as assessed species. 28% of those are threatened. That's what these numbers are showing here. So where exactly are we getting these numbers from? Well, they come from the IUCN Red List, which is an international inventory of the global conservation status and extinction risk of biological species. Okay, so who creates this list? The International Union on Conservation and Nature creates these lists, and they are an international organization working in the field of nature conservation and sustainable use of natural resources. It's important to note that they have global authority on the status of the natural world and the measures needed to safeguard it. The IUCN lists are continuously updated, changing the status and adding or removing species from a certain category. So here, every assessed species fall within this category. We have least concern. These are species that we just have no concern for extinction. Great, perfect, love that. And it ranges all the way to extinct species, which these are species that no longer exist on the planet anymore. Between that range, we have what is known as near threatened species, and these are just species that are vulnerable to endanger in the near future. However, they don't currently qualify for a threatened status. And then we have the next 3 categories: vulnerable, endangered, and critically endangered, which some of you may have heard some of these terms. These together make up what is known as threatened species, where vulnerable species have a risk for extinction in the wild. Endangered species have a higher risk, and critically endangered species have the highest risk of extinction in the wild. After that, we have what is known as extinct in the wild species. So these species only survive in captivity, and they no longer exist in the wild. If you're curious about the specific criteria of each one of these categories, you can find them on the IUCN website at IUCNRedlist.org or on the IUCN Red List Wikipedia page. I'm not gonna lie, this is when it gets real, these next 2 slides. And it's kind of like the whole point of this entire presentation is in these 2 slides. I'm not trying to discredit any of the information said or the importance of the information that has said. I just want you to know that this is the time for us to wake up, to open our eyes and fucking do something about it, okay? I'm creating educational content to do something about it, okay? We all have ways to do something, okay? When a high percentage of species dies out across the board, it is known as a mass extinction event. In Earth's history, a mass extinction event has occurred a total of 5 times, all of which were caused by events that organisms did not have knowledge that they were doing something wrong. For example, at the end of the Triassic, the seafloor started spreading, caused a mass extinction event. This caused an increase in CO2, which caused a lot of global warming. Sound familiar? This CO2 then acidified the oceans, along with the oceans becoming warmer, causing the death of many species. Sound familiar? This was, by the way, the 4th major mass extinction event, and it eventually created the Mid-Atlantic Ridge, creating the Atlantic Ocean and separating North and South America from Europe and Africa, and in this process caused the supercontinent of Pangaea to break up. Today, extinction rates are now between 110,000 times higher than the background extinction rate. And no, the seafloor isn't spreading in the same way that it was at the end of the Triassic. And no, an asteroid is not about to hit us. So what really are the causes of the Holocene extinction, or the sixth mass extinction that we find ourselves in? Well, they are all things that, one, a single species is doing intentionally, and two, could be avoided and even reversed if we stopped and or make the environment our priority before anything else. We are not technically in the extinction, but if nothing else changes and this proceeds to continue to happen, in the history books, this period that we live in right now, recording this in 2025, whenever you're watching it, I presume to be in 2026, will be known as the years during the midst of the sixth mass extinction. This is all because of the remaining information on this slide. 1. The unsustainable and inefficient use of our land, water, and energy, where 40% of our land is dedicated to inefficient use of agriculture alone. Number 2 is because of habitat loss. That is the elimination of natural environments and is the leading cause for the loss of biodiversity seen across the globe. In this picture here, we can kind of see that happening. This once was a picture of the Amazon rainforest. You can see here, there's an extinct line. This probably goes across like right here. I can't really see because of the clouds. And this all has already been lost. So what is happening? So trees are being cut down, then the land is burned, and what used to be the most biodiverse place on the planet ends up being farmland. And the trees are being sold for any paper products. Among with this, there is a whole host of issues occurring because of our direct effect, which I won't have time to get into in this video, but we shouldn't be doing this for many, many reasons. The third reason that this mass extinction is happening is because of climate change. Again, which is the dramatic change in climate, mainly driven by global warming and us artificially changing the environment. Here, we are artificially changing this environment. 4 is pollution, and in particular, the creation of plastics and forever chemicals that break down and accumulate in every single living system on Earth. And 5, but certainly not least, is overexploitation of species through farming, hunting, and overfishing. And that is what the left side of this figure is showing. Through many ways, humans are artificially increasing our greenhouse gases, specifically CO2, into the atmosphere. This, again, is going to, 1, warm the oceans and also acidify it. That alone was the cause of the 4th mass extinction event. I just want to put that out there. We are also polluting our environments through waste, causing algae blooms, again, through plastics, which is causing dead zones in the ocean and on land. Again, coral is dying because oceans is getting too hot. Among all the other ways we have already seen in this video, we are killing the earth. There's no ands or buts if it's humans or natural causes, and there's no ands or buts if it's occurring or not. It is occurring, whether or not we see it directly where you live or through educational content such as this. Other places around the world have already started to see the direct effects of humans. Okay guys, this slide alone might get me in trouble, but I don't really fucking care. To put this video into a nice, neat little bow, and if you crunch down the numbers of across the board for all the reasons, account for everything, climate change and the 6th mass extinction event are undoubtedly caused by human activity and are primarily caused by following 3. Corporate greed, which is the excessive pursuit of profit, period, and wealth by corporations, often at the expense of ethical standards, employee welfare, consumer interests, and environmental sustainability. Oh, there actually should be a period right here. 2, by consumerism, which refers to the continuous acquisition of goods and services in an ever-increasing quantities. We don't have to buy shit. Stop buying shit. Circle economy, build our own stuff, okay? Stop letting corporate greed trick you into buying stuff that we don't need. I don't know how else to say that. And 3, caused by the lack of, very important, the lack of environmental policies, which are sets of principles, strategies, and actions designed to manage and protect the environment from the negative impacts of human activities. This figure here shows all the things that we have talked about today, all of which industries have not set any suitable environmental policies and are generating a large carbon footprint just so they can obtain larger profits. And so, in the creation of power, in manufacturing goods, in powering buildings, in producing food, using transportation, cutting down forests, and consuming too much. These are all direct causes that a single species is having on the entire planet. I hope now that everyone is starting to understand if we continue with how we are doing things today, we are not going to make it to the next century, let alone have a hospitable future for our future generations. We're all connected to nature, and what we do today will shape the future for thousands of years. As of December 2025, the US administration removed human causes of climate change from the EPA website. What's the EPA? The Environmental Protection Agency. And if that doesn't say anything about how the state of the US current affairs is, I don't know what else will. The Environmental Protection Agency is saying that humans are no longer the cause of climate change. Through this video today, I hope you understand that humans are directly the cause of climate change. And in this picture here, I just want to show you the cause. Many of you don't see the effects of climate change until it's too late. This is just a mound of trash. Where is this trash coming from? What companies are producing it? Why aren't they caring about the end of life of these products? The vast majority of which are plastics. Plastics that are going to stay for hundreds of years. And these companies keep on producing like it's no one's business because the numbers go up. Unfortunately, many companies currently prefer short-term profits over long-term suitable futures. That's it. Anyways, I can go on and on and on. So please check out some more videos if I have them produced. Thank you for watching and listening to my tech talk and letting me explain the much larger story that Figure 1 was trying to explain. I hope to see you in the next video, and that everyone is going to have a great rest of your day, and know that I love every single one of you. And now, here are my sources.